Let's take a look at example 6. We won't be doing a whole awful lot using the one-sided derivatives in our class, but certainly where we do want to use them is to kind of investigate the behavior of f of x equals the absolute value of x minus 2 at x equals to 2. And we're actually going to use them to show that the function is actually not differentiable at x equals to 2. So let's begin by looking at first, let's say at the left-hand derivative at 2. So we just saw this definition a little bit ago, but the left-hand derivative of f at 2, this is equal to the limit as x approaches 2 from the left of f of x minus f of 2 all divided by x minus 2. And this is that alternative formulation of the derivative we just saw a moment ago. F of 2 as a value is pretty easy to compute. If we plug 2 into this function, we get the absolute value of 2 minus 2, which is the absolute value of 0, which is 0. So this is going to be the limit as x approaches 2 from the left. We have a subtraction by 0 up top. And now we need to investigate f of x. And this is another time where we've seen this before, but we need to kind of go back and think about the definition of the absolute value of x minus 2 as a piecewise defined function. Remember, the way that absolute value works is it's equal to the positive of the quantity on the inside, or it's equal to the quantity itself, when that quantity on the inside is positive. So it's x minus 2 when x minus 2 is greater than or equal to 0. If we take this test condition and solve it for x, add 2 to both sides, that simply happens when x is greater than or equal to 2. But it's going to be equal to the negative of the inside quantity. After all, it has to switch the sign. And likewise, you do the same thing, check the test condition, but that's going to happen when x is going to be less than 2. And the way this is going to play into our one-sided limits is we're right now looking at the left-hand derivative at 2. So we're looking at the limit as x approaches 2 from the left. That is, we're coming in from values that are going to be slightly less than 2, so we're going to be using this portion of the function. So wherever we see f of x, we're going to replace it with the negative of x minus 2. This is equal to the limit as x approaches 2 from the left. We have negative x minus 2 divided by x minus 2. Notice that the x minus 2's cancel, and so we get the limit as x approaches 2 from the left of the constant negative 1, and the limit of that constant is simply going to be negative 1. So the the left-hand derivative at 2 has a value equal to negative 1. Now let's take a look at what happens as we look at the right-hand derivative. I'm just going to be a little bit brief about it, but the right-hand derivative, now we're going to approach 2 coming in from the right-hand direction. When we approach 2 coming in from the right, so now we're coming in from this side, notice that if you're coming in from the right-hand approach, these are values that are going to be to the right of 2, or values are going to be greater than 2. So we can replace the absolute value of x minus 2 simply with x minus 2. So from the right-hand approach, f of x is just going to be x minus 2, which means we get the following. This is going to be the limit as x approaches 2 from the right of x minus 2 divided by x minus 2. These cancel, leaving us with the constant 1. So it's the limit as x approaches 2 from the right of a constant, which is just that constant value of 1. So the right-hand derivative at 2 is equal to positive 1, and what that means is that the derivative at 2 in general does not exist. The reason why f is not differentiable at 2 is because the value of the left-hand derivative is different from the function's value of the right-hand derivative. And graphically, we can see this. If we go ahead and graph the absolute value of x minus 2, it's just your classic graph of the absolute value, but it's going to be shifted 2 units to the right. And that's what gives us kind of that V-shaped nature. If we look at the graph to the left of 2, it looks like this kind of piece of this straight line. And that straight line would have a slope equal to -1, i.e. that's what we saw when we looked at the left-hand derivative. But if you look at the portion of the graph to the right of 2, this looks like this straight line, and that straight line has a slope of +1. And what we get at x equals to 2, where those two things meet, it creates this sharp corner. And anytime, if you look at the graph of a function, if it has a corner, those will be places where the function will not be differentiable. Okay. So this function is not differentiable at x equals to 2. Let's take a look at example 7. Suppose f of x equals x to the 1/3 power. Is f differentiable at x equals to 0? Well, let's find out. The derivative at 0, here it's not a piecewise defined function. So I can just use the following. I'm just going to use the limit as x approaches to 0 of f of x minus f of 0 divided by x minus 0. This is going to be equal to the limit as x approaches to 0. F of x is x to the 1/3 power. F of 0, if you plug 0 into this function, that's 0 to the 1/3 power, which is equivalent to the cube root. Cube root of 0 is 0. So this is going to be 0 divided by x minus 0. So we get everything plugged in. This is equal to the limit as x approaches to 0 of essentially we have x to the 1/3 divided by x to the first power. This is division by like bases. You can simplify it by subtracting the exponents. This would give us x to the 1/3 minus 1 would be the -2/3 power. So this is equal to the limit as x approaches to 0 of 1 divided by x to the 2/3. If we try to plug 0 in, you're going to get 1 divided by 0 to the 2/3, which is going to be 1 over 0, which is going to be an infinite limit. So this limit does not exist. It's actually approaching positive infinity. So what that tells us is that f of x equals x to the 1/3 is not differentiable at 0. So the conclusion is no, it's not differentiable at 0. And why is it not differentiable at 0? Well, again, this limit becomes infinite. And so what happens is this graph actually has a vertical tangent line at x equals to 0. So this is the graph of x to the 1/3 power. So here's x to the 1/3, and if you look at the order pair 0, 0, which is right here, at that point, we're gonna have a vertical tangent line. And I might not have done the best example of drawing it. If you kind of zoom in really closely around 0, should look a little more vertical-ish. So as it comes in, it's gonna look something like this. It's coming in, and then it very nearly goes vertical for a moment at x equals to 0. And that's what gives us that vertical tangent line. Okay. Together, a couple of different things that this kind of points out. So first of all, functions are not going to be differentiable at every single point. In particular, one of the takeaways is if you have a sharp corner, or later on we'll probably see things that have what's called a cusp. A cusp is kind of like a rounded style corner. So if I just kind of draw it like this, these are called cusps. Those would also be places where a function would not be differentiable. So any sharp turns or corners, the graph will not have a derivative, and it won't be differentiable. Similarly, if you have a place where a function has a vertical tangent line, functions are not differentiable wherever we have a vertical tangent line. Okay. So those are places where you don't have a derivative. However, if you at least look at both of these functions, the absolute value of x minus 2 and also the cube root of x, or x to the 1/3 power, those functions are continuous everywhere. And kind of what this tells us is that you can be continuous without necessarily being differentiable. But theorem 3.1 says that the converse of this is the following, that if you are differentiable, then automatically that makes your function continuous at the point. So for any function that's differentiable at the point x equals to c, then automatically that function will be continuous at x equals to c. So in many ways, differentiability is a stronger condition than what continuity is. Because if f is differentiable at c, then that automatically applies that f is continuous. And as we saw in the previous two examples, be very careful, the other implication does not hold true. There are functions that are continuous at points, a la absolute value of x minus 2 at x equals to 2, and x to the 1/3 at x equals to 0. Those functions are continuous there, however, they are not differentiable. So just know that differentiability implies continuity, but not the other way around. It's not an if and only if statement.